sorry. Yeah, so the basic question that we're going to ask today is, what do you mean by asymptotic flatness? Or when would you call a space-time asymptotically flat? And how do you preserve asymptotic flatness? So we know that the usual flat space, when we talk about the usual flat space, we often talk about the symmetries of flat space associated with it, like the Poincare symmetries. And today we'll see that if you want to impose some conditions called asymptotic flatness conditions, which are basically things which you impose far away from any sources, then what are the symmetries that exist in that space-time? That's the basic set of questions that you want to ask. That is, symmetries of flat space-time far away from sources. Okay. Now, I think this was originally explored in this work by BMS in the 1960s, but it was brought into the string theory community by Strominger in 2013 or something, when he showed that you could use asymptotic symmetries and the conserved charges of these symmetries in order to derive things called soft theorems. So soft theorems are things which you usually hear in some particle physics talk or in some QFT1 course or something. But Andy showed that there was a relation between the asymptotic symmetries which you could derive and soft theorems, which was already known from Weinberg's papers in 1970s. This was some work which was established in 2013. And then again, in a few years from then, like I think 15 or 16, there was also some work by Andy and Zobedov, which showed how this was related to the memory effect, which is another corner, which is an effect which is usually studied by the gravitational wave people. And we'll discuss memory effect in some detail tomorrow. And this was again a connection that was shown sometime in 2015 or something. I don't remember the exact year, but it's somewhere around then. So this actually completed a so-called triangle, which is now known as the infrared triangle, and it deals with the so-called infrared properties of some theory, where one of the corner is the asymptotic symmetries, one is soft theorem, and the other is memory effect. And this triangle is basically a set of mathematical operations which relate these three. So the way, however, I got into this subject was by a completely different story. It's a story which you'll hear a lot more about from some talk by Siddharth, I think, in a coming week or so. And that's the notion of what's called flat holography. So I'll not talk about this in any detail now, but this was first discussed in this paper by Sovrat and others last year, where they talked about how one can get a notion of holography in flat space. And so this thing was worked out in 4 dimensions for massless theories, for massless particles. And yeah, and the way I got into the subject was to understand how you can think of generalizes or understanding this in higher dimensions. So for example, if you wanted to ask how holography works in 6 dimensions or something, then you would, it turned out that you naturally had to understand how asymptotic symmetries work in 6 dimensions. And while doing that, we found out that that question was not completely answered in 6D. And I'll tell you what exactly was not answered and how we have got some understanding of that now. So anyways, so for this, I think you'll hear a lot more about from Siddharth in a couple of weeks. But let's just begin trying to understand what asymptotic symmetries are. Let me open my notes. Right. So the first things first, we need to fix a metric in which we're going to work in. By the way, everything that I'm going to say has got a QED analog as well, but I'm going to talk about gravity. I initially thought I'd discuss QED and then go to gravity, but I think it's equally good if we just talk about gravity first. So let's first start with a metric which we're going to work with. And before that, I should mention that everything that I'm going to talk about will be in flat space-time. there are some developments also in de Sitter and anti-de Sitter spacetime, which you should feel free to look into. But for now, let's just talk about flat spacetime. And the metric that we are going to work with can be written in this nice gauge. Let me first write down the components, and then I'll explain the gauge choice and so on. So my space-time indices are going to be G mu nu, and the this is going to be this column is going to be the retarded time column, which is U. This is going to be R, and this is going to be the sphere component, which I'll use small Latin indices to denote. And I'll always be working about future null infinity. So I think this is something you already know, that the Penrose diagram of flat spacetime looks like this. And our interest will be towards theories living at I plus. There's a completely equivalent description for describing I scry minus, which we're not going to do today. But the formulas are very similar. And we are also interested in massless particles. So the discussion of I plus will not be that important for us. But there has been a lot of development also in studying symmetries and I plus. But we'll not be discussing that today. And neither will spatial infinity be important for us. At some point, I'll mention how spatial infinity has helped understand a few things, but it's not going to be important for the major part of our discussion. Okay, so the inverse metric is given as follows. It's quite simple. Okay, and as you notice, a few components are set to 0. These are what are called the Bondi gauge choices, which sets GRR and GRA to 0. Along with this, you've got another choice which completely fixes the small diffeomorphisms, which is basically this choice. It just fixes the determinant of GAB, and I'll explain how this choice becomes important later on. So gamma AB is the metric on the 2 sphere. Okay, in 4D. So yeah, we'll in general work in D plus 2 dimensions. So in general, gamma AB would be the metric on the D sphere. All right. Now, of course, this form might not be familiar to you all, but I'm sure the form that will be familiar is this. If I just write in terms of ds square, and I write the leading order components, I'll explain what that means. Then this is the background metric of the theory. Sorry. Okay, I'm sure you'll all have seen this metric. Now, this is the background metric. And okay, and this full G mu nu has got these additional components which look like M, beta, U, UA, and so on. And all of them can be defined using some fall-off conditions. So like I said, this is a metric which is usually convenient to study the theory at scry plus. So you need to understand how things fall off as you go to large distances, and distances measured by small r. And therefore, you can define all of these components as a series in R. Series as you take R tends to infinity. So for example, if you look at beta, then beta looks like this. Notice that n equal to 0 in here would just be this value, the coefficient of du dr, which would be 1. Sorry, minus 1, should be minus here. And then n equal to 1 and so on can be found from the equations of motion. So the fall-off conditions that we take in here are quite liberal. All we demand is that any corrections to this metric should appear at the order 1 by r, which is the least you can do. So let me just state this for completeness. And GAB, like I said, goes as R squared gamma AB, and GABN R bar N. Okay. Now, there's just one thing I want to mention. It's not going to be that important, but it's often helps in simplifying some things. And that's the value of M0. So M0 is the coefficient of 1 by R bar 0 and the expansion of M, and which basically hits this guy, like it's the coefficient of du square at the leading order. And what you can, and M0 has a choice. So in the metric that I've written here, M0 is just -1. And you can show that it's -1 when gamma AB is the 2-sphere metric, or rather the d-sphere metric. All of this is true in every dimension. The d-sphere metric, but it's 0 if gamma AB is chosen to be equal to delta AB. So there's a coordinate choice which you can make such that the background metric looks like -2 du, -2 du dr plus r squared delta AB dz a dzb. It's just a coordinate system which one can work with if needed. It often helps in simplifying some stuff because you don't need to then deal with the covariant derivative of the sphere and so on. But anyway, everything that I'm going to talk about in 4 dimensions soon will be in the sphere metric, in the familiar metric to all of you, but some results in 6 dimension I'll allude to in this metric, but conceptually there's no big deal or no big difference between the two, and there exists a coordinate transformation which you can perform to go from one to the other. Okay, now first things first is like what exactly does this gauge condition imply, let's say for asymptotic flatness? One might wonder as to whether, assuming such fall of conditions for these components will induce any change in the Ricci scalar or something. We know that the Ricci scalar must be 0, but in general, will it change it? And it can be verified for, let's say, source-free theories. Suppose you don't have any sources, and the only source you can expect is from gravitons themselves. Then they would satisfy this equation. Okay. So you can easily see that using the gauge condition RR and GRA equal to 0, you just end up getting RR equal to RRA equal to 0. And then if you compute the value of the Ricci scalar R, that looks like GUR, RUR plus GAB, RAB. Okay, this is just following from the inverse metric that we have. Now, let's take the next Einstein equation, where I take mu equal to UR. So that would then give us RUR minus half 2GUR RUR plus, which would then imply GAB RAB equal to 0. Okay, so you automatically see that one more component goes off. Again, this is simple to see by noting the form of GUR. It's just G upper UR and G lower UR just cancel each other. Sorry, there should be a plus to beta. One of them should be, this should be plus. Yeah. Okay. Then let's take the AB component.
Hey, Chandra, did you write a use curve with the time compound of the metric, or is it what?
So this is the retarded type. Yeah, so good, very good. So I should have mentioned this, thank you. So U squared that is in here, that looks like GAB UAUB, okay? And at the leading order, G upper AB goes as 1 by R squared. So this begins at order 1 by R squared. Therefore, the initial term that you have here, the du squared, that's not affected by this guy. Okay. Now, Akhil, was that your doubt or?
Yeah. Thanks.
Okay, great. Thank you.
Sorry, Chandra, I missed a bit in the beginning, but so
Yes.
just want to ask, in the Bondi gauge condition that you've written, where you've enforced this determinant condition,
Yes.
isn't the condition usually like the derivative with respect to R of the GAB by R square 0, and then an additional restriction on the space of solutions is that the the determinant is the determinant of the sphere metric. Isn't that the statement?
No, I think you're right. Good. But isn't it true that if you assume this already, then you end up getting the derivative of R equation also true? Because the RHS is independent of R.
That forces the derivative of R also ensure that the shear is traceless, right? This does not necessarily enforce that.
Indeed, you're right. Thank you. You're right. So your thing is that you should also add this condition.
Right. And then the leading determinant, the leading expansion in the GAB, that is the determinant of gamma AB.
Correct. Indeed. Thank you very much. Yes. Yeah, I was actually thinking in 6D, because in 6D, the tracelessness does not require this extra condition. But yeah, in 4D, I think it does. Yes, indeed, you're right. Thank you.
Chandramouli, there are a couple of questions in the chat. I will read them out.
Yes. Let's see.
So the first question is, do none of these parameters have any spherical dependence?
Oh, they do. They do. All of them will have. In fact, we'll solve for some of them very explicitly and discuss what they are. Yeah.
The second question is this the asymptotic form of the metric? Is the bulk also flat?
The bulk need not be flat. You could have sources in the bulk. This is the asymptotic form of the metric. So if you do have sources, we'll assume that it falls off sufficiently fast. Yeah. Okay.
Sorry, did you mean these Einstein equations are only imposed towards the boundary? Is that what you said now?
So we will. So the Einstein equations that we'll study, we will also study them in R by R expansion. Indeed. This is an Einstein equation which I was just doing to show you eventually that you'd end up with capital R equal to 0. But that thing would change if you had sources which fell off as a particular power of small r. However, later, when we have to individually determine these components of the metric, let's say if you have to determine GABN or the solutions for MN and so on, then you'll also have to, then we'll be solving the Einstein equation order by order in capital in small r. Yeah. Okay, any further questions? Okay. Okay, great. So like I said, for the source-free Einstein equation, what you just see is that, yeah, where were we? Right. So now if you just choose mu equal to AB, it's actually very simple to show that you'll also end up getting GUR or UR is 0, and GUR is generically not 0. In fact, it starts off with -1. So RUR is 0. And therefore, the equations that we will be solving eventually are just this. Okay. Good. Now now what I'll do is, like I said, everything till now are valid in all dimensions. There's a small catch when it comes to odd dimensions. So like I said, we'll specifically talk about 4D and 6D today. But for odd dimensions, what happens is you often end up getting fall-offs which are not integer powers. That is, you might have some fall-offs which are logarithmic, not logarithmic, sorry, the fractional powers, like 1 by r power 3 by 2 or something of that sort. And so sometimes there are some issues which you might encounter, which says that there are branch points and so on. So odd dimensions have to be dealt with a little more care. We'll again not be dealing with odd dimensions in this lecture, but there has been some progress in understanding odd dimensions. Like, for example, in ADS3, you can find some papers by Compare, which does it. In fact, in Compare's lecture notes, he has got a set of symmetries which discuss, sorry, not ADS3, I mean flat space 3. And I'm not so sure if there has been a lot of progress in higher dimensional things. But there are some other papers by Wald, Tanabe, Shizuki, and others which talk about odd higher dimensions. But yeah, that won't be our concern as of today. So now I'm going to completely restrict to 4 dimensions. And first discuss like what the asymptotic symmetries in 4 dimensions are. And then I'll explain how that generalizes to 60 and what are the problems that which arise as you try to generalize that in 60. So I think this part might be known to all of you, or maybe most of you, if you've followed this thing. So in 4 dimensions, let me write down some of the solutions of the Einstein equations that we need. So I'll directly write it down in terms of the metric. This was the one which we started with. 2r squared gamma z bar. So the z bar coordinates are the ones which are so-called defined in the celestial sphere. There's a coordinate transformation which takes you from ds squared equal to minus dt squared plus dx bar squared to these coordinates. The transformation is not going to be useful for us at all, but if you're interested in the details, feel free to look at Andy's book. He has all these details. But for now, that's just another way of parametrizing the 2 sphere. That's it. This is the next order term in du square. We've got r czz dz squared plus okay. Now I'm putting these terms in dots because we'll not be needing them. However, if somebody is interested in higher and higher order effects, they would have to study what those dots are. These GUZs are the same thing as the capital UAs, which I wrote above. So if A was either Z or Z bar, UZ would be GUZ. That's it. And it's just given as half DZ CZZ plus order R minus 1. Okay. Right, and dz is the covariant derivative on the sphere. MB has a name. It's called the Bondi mass aspect. We will discuss this in some detail after we talk about the charges. And the basic idea of MB is that it, let's say, for if you had a curl like space-time, and then you brought it to this form, then you would find that MB is proportional to the mass of the object inside. So anyways, MB has some more significance, which I'll explain later. Now, along with this, there's another tensor which is important, which captures the radiation content of space-time, basically the gravitational radiation that you have. And that's just given as a derivative of CZZ. That's defined as the News tensor. And MB is del U CAB. Okay. So in 4 dimensions, the free data of the theory is specified by CZZ and CZZ, Z bar, Z bar. By free data, I mean you can, up to some integration constants or so-called multiple moments. Let's just call it integration constants for now. So up to some integration constants, you can determine every other term in this expansion in terms of these variables. Okay. So along with the boundary conditions, if you specify the profile of CZZ and CZ bar, Z bar, then you're done. That specifies your phase space completely. Okay. And in terms of this News tensor, if you study the RU equal to 0 equation, then you could write down the evolution equation for MB. That just is given by this component. Sorry. Okay, we'll get back to this expression in some time. This this MB is also going to be important for us if we want to write down an expansion, if we want to write down an expression for so-called the super translation charge. But for now, let's just think of it as an Einstein equation. Okay. Now we want to discuss the symmetries of the theory. Like I said, we can always.
So Chandramouli, let me just interrupt you for 1 second to just summarize what you've done so far. I understand that you have written a form of the metric, which you're calling like this is the asymptotically flat metric. If it's you've written it in a particular gauge, and you said, okay, these are the follow-up conditions, then I'm going to call it asymptotically flat metric. And then you've written down Einstein equations in the end, which gives you like an evolution equation.
Yes.
And from that, we can see that basically it's only if someone knows this n ZZ bar components, then the evolution is fixed. Is that right?
Exactly. That's right.
Yeah. So that's why you're calling this like a free data.
Yeah. You'll also have to give the value of MB at the boundary points, of course.
Right.
But like I said, up to some like along with the boundary conditions, if you know the radiation content, you're done. That's what I mean.
Okay, please go on.
Yeah, actually, I should have also mentioned.
Chandra, could you?
Yeah,
Chandra,
go on. Yeah.
Could you repeat what is this GUZ equal to del Z CZ Z condition?
Yeah. I was actually just going to say that. Thank you. This is not a condition actually. This is just implied from the RA equal to 0 equations. If you just plug that in, you end up getting GUZ and GUZ bar. I'm often suppressing the Z bar equations, but they're exactly similar. In 6D, I'll write everything in terms of AB. So that's going to be a bit clearer then. But anyway, this is not an extra condition we impose. It's just if you solve our A to the leading order, you would just see this. Okay.
Can I ask a slightly naive question? As in, like, so whatever you're doing till now, you're going to some first few orders in this R expansion, right?
Correct. We just need the
But
first few orders.
The metric ansatz you introduced first seem to have exponentiated various things and so on. So is that motivated?
So, okay, the exponentiated thing is just for writing down the series in some nice way. I do not know if there's a bigger motivation for writing E part 2 beta, other than the fact that the leading order term for this is 1. I mean, this is the only exponentiated term you can have. You could have called E part 2 beta as V, let's say. Nothing would have changed.
I mean, you have split the series into this exponentiated part and the series for M and so on, right? So I was just wondering if that's like more motivated. Yeah. Okay.
Sorry, what's?
I mean, secretly, this M series and beta series are like is defining. Okay, there are independent beta terms, e⁻² beta terms also. I see.
Yes, indeed. So this. Oh, I'm sorry, my handwriting is atrocious, but this is beta n. If that's what you mean, like.
Yeah, but beta itself is not a. Yeah, I mean the way
so
it is
all of these things are expanded in R.
Yeah, thank you.
Like instead of E part 2 beta, you could have just put V, for example. Just put a V here. Nothing would have changed. You have to just remember that V starts from -1 then, because of this, because that's the leading order metric. That's it. Okay. Okay, great. So now we're going to discuss the transformations which preserve our gauge conditions, and basically what also define asymptotic flatness for us. So the gauge conditions that we have are, say, these three Bondi gauge conditions, and then if you want to ask which transformations preserve them, then what we would do is we take, say, GRR, and we apply any arbitrary diffeomorphism on that, and we would like it to be invariant under that condition. So this would imply that some d derivative with respect to some vector xi acting on GRR should give you 0. Similarly, these conditions should also hold GRA equal to 0, and also this should be equal to 0. And I'm not solving it here, but it's kind of trivial to solve them. if you just expand them. In fact, it's possible to solve them to all orders in R. And while discussing the 6D case, I'll state that solution. But just for simplicity now, let's just state a solution to the particular orders of R that we will need here. And that's just given as this. So xi u, the vector xi u is written as f. Xi r is written as, I should mention that they're the solutions. Xi r is given as -1 by r. Sorry, this is dz, dzf. Xi z is -1 by r dzf. And similarly, xi c bar is -1 by r. Okay. So again, these are the solutions which preserve it up to some particular order of R. But all of these can be expanded to further orders in R. And there's a more general formula which can be given, to all orders of R. And we'll do that later. For now, this is just a very simple set of formulas that we have. And here, the most important part is that the function f is u independent. And it's only a function of z and z bar, basically the sphere coordinates. So f is only a function of the sphere coordinates. And these are what are called the super translation generators. I'll explain why we call it super translation generators. But let's come to that in a second. So the way we see it is by taking GAB and studying the variation of GAB to the leading order in R. And what we find is that delta f, CZZ, often the variation is written with delta. That's a symbol that I use continuously. That's written as f nzz minus 2 dz square f and delta f nzz. This is the new tensors given as del u nzz. Okay, just to remind you, nzz is the same thing as del u czz. Okay. So notice that if you take f to be a spherical harmonic or proportional to the spherical harmonic, you have to exactly go to the sphere coordinates to see how it's in the spherical harmonic thing. But if it's proportional to say y0, 0 or y1m, where m can take -1, 0, 1, this would imply that delta f czz is 0. Okay. That's just because y1m is proportional to 1 part of z, and y0, 0 is proportional to 0 parts of z. So this term will annihilate them, and therefore this term never contributes in this. Like there's no non-trivial contribution arising from this term, which actually tells you that this is the first place where you realize that f beyond L equal to 1 plays an important role. Okay. So anyways, good. So now that we have mentioned the symmetries or the symmetry generators of the theory, we would obviously like to ask what are the conserved charges corresponding to these symmetries. And in order to define the conserved charges corresponding to symmetries, we use the Noether theorem. However, for gauge theories, the Noether theorem is slightly more complicated to state, but the basic formalism is similar. We would first write down what's called the symplectic form of the theory, and using that, we'll get the Noether charge. So if you haven't ever seen the symplectic form before, let me just give a lightning review of what we mean by the symplectic form. It's basically a structure. It's basically a two form, and it's basically a two form. Again, we don't need to use form notations or anything to any great detail. We just need to realize a few properties of this. Anyway, so the symplectic form is a two form which helps us determine the Poisson brackets. That's one way of thinking about it. I'm not quite sure whether it was discussed for the first time, but in the way in which I'm going to present it is there in this paper by Witten and Cherenkovich. And it's a very simple way of, I feel it's a simpler way of talking about it. But if somebody's interested in the mathematical details, I would encourage you to look at this paper by Zuckerberg. Or that was a spelling. Okay, I'm forgetting the spelling. But yeah, there's a paper by, sorry, I'm saying a wrong name. Zuckerberg is the Facebook guy. Zuckerman, sorry. So sorry, Zuckerman. It's called Action Principles and Global Geometry. Okay, some paper from 1986, which deals with this in great mathematical details, but it's not going to be that important for us. So anyway, the symplectic form for us is just an object which generates a Poisson bracket. So for example, if you wanted to write it for a scalar field, look like delta phi wedge, delta pi mu. Now, the reason I'm writing in terms of the wedge product is mostly for convenience. There might be there's probably a deeper mathematical reason for it, but it's not going to be important for us. The only convenience that we see here is that if you think of this in some matrix form, where you write this in this usual row times a big matrix times a column, and you think of this matrix as omega ij, then this takes the value of 0, -1, 1, and 0. And what it helps in doing is that if you want to define the Poisson brackets of, say, some quantities A and B in your theory, which would look like dAdq times dBdP minus dAdP dBdQ. This is for phi equal to Q and pi mu equal to P in classical mechanics. Then you can just simply think of this as AI omega ij bj. Okay, that's one advantage of writing this in terms of the wedge product. And of course, if it's written in terms of the wedge product, then we'll assume that del square is 0, since it's treated like a exterior derivative in field space. But the way we get to this expression is something which we've all done many times while studying the variation of the Lagrangian. So again, I'm going to assume that the Lagrangian of the theory only contains either the fields phi or its single derivatives. However, this is not an important restriction. We can do it for a Lagrangian which has n derivatives of the field as well. It's just that you have to define these variations a bit more carefully. So if we just assume this for now, which is a bit simpler, and we take the variation of this Lagrangian, then in the usual derivation of the Euler-Lagrange equations that we have, we'll just end up with this. And then we perform the same usual tricks which we do while defining the Euler-Lagrange equations. That is, we commute the d and delta, sorry, the partial derivative in delta, and we write this as delta phi times del L del phi minus del mu plus a term which looks like a total derivative, and that just happens to be del L del mu phi times delta phi. This object, let's call it theta mu. It has a name. It's called the pre-symplectic form. And okay, I'm not sure why Wald introduced so many names, but what it helps in doing is, if you take a variation of this, you just end up getting j mu. So notice that del L by del L del mu phi is basically pi mu, the usual definition of the canonical momentum times del phi. So if you take another extra variation of theta, and remember that these variations are treated as Grassmann objects, then delta theta mu basically gives you this. Okay. And this, when integrated over the Cauchy slice, So let's say you integrate delta theta mu over some Cauchy slice d sigma mu. This is what defines the symplectic form of the theory. So, okay, great. Right. Now, of course, the symplectic form helps us understand what the canonically conjugate variables are. We could have also done it just by writing what pi mu was, but the symplectic form helps us do it in a slightly more convenient manner. It's also convenient for one more reason, because it also helps us get the definition for the Noether charge. Now, usually when we define Noether charge, we just take the 0th component of this variation. Let's say you take theta 0. You want to consider the, let's say, charges corresponding to a time-like surface or something, a space-like surface, which you have to integrate with some d sigma. And you would define some charge like this. But now what we're doing is we're taking another additional variation on theta. So instead of getting q directly, what we'll end up getting is delta q. So the definition for the charge. And this is the part which I said is kind of mathematically convoluted, but I think I don't, like in our thing, we won't ever have to use those deep mathematical properties. So it can be just thought of as a simple extension to whatever we've already learned before. Anyway, so this is just omega. Sorry, you have to just write omega with delta and delta xi. Now, what this notation means is the following. So here the delta xi is going to be a symmetry, a variation corresponding to a particular transformation. For example, if you're taking time translations, then delta xi would basically give you that. And this delta is this extra additional variation that we have taken in this step. And therefore, because of this extra additional variation here, you would have a delta and q. And this is, capital omega is defined in terms of theta mu in a very simple way. It's just delta theta mu delta xi minus delta xi theta mu delta. That's it. And if the charge is integrable, then often what happens is this object here reduces to a delta of something. Okay, it just reduces to a variation of something. And in the examples that we are going to discuss, in fact, at least in the examples which I have seen in the literature, I've always seen integrable charges. However, if the charge was not integrable, then what would happen is this would not reduce to a term of this form. You would, like, basically you could not write it as a total variation. And then you would have to think of how you integrate in field space. Since these variations are taken in field space, you'll have to worry about how you integrate those. But like I said, I'm sure they are relevant for some examples, but I have never come across those examples. But if you're interested, please look at Compass notes. I think he refers to some other literature which uses these extra definitions. Okay, any questions about this? Not sure if I went over this too fast or it was already known to all of you. Okay, great. Great, so now, now that we have defined the symmetries in this theory, we need to understand the charges for charges corresponding to them in gravity. And for doing that, we first write down the symplectic form. And in order to write down the symplectic form, you have to write down the symplectic current. Symplectic form is just an integral with the symplectic current, so it's nothing very deep. So the analog of delta phi wedge delta mu in gravity is what? In order to write this thing down, it's convenient to work it out in where the action is only composed of g mu nu and single derivatives of g mu nu. If you have double derivatives, then you have to work a little more. But we don't have to do that, at least for the Einstein-Hilbert action. I'm not sure if for other theories of gravity, you've got the simplification. But in Einstein-Hilbert action, what happens is by adding a boundary term to the action, you can actually convert the Lagrangian to a more convenient form, which is often called the gamma-gamma form. And that looks like this: minus g mu nu, g mu gamma alpha mu beta, gamma beta mu alpha minus. Okay. This is a much more convenient form to write the Lagrangian in. I'm sure it's there in many places. The place where I saw it is in Landau and Lifshitz in section 93. Landau, Lifshitz, I think in the classical theory of fields. So if you haven't seen this before, feel free to look at that. And after writing the Lagrangian in this form, it's very easy to read off a form which looks like this. And if you just compute the value of J alpha, again, this expression for J alpha is given in many places, like Witten's paper, for example, so on. It looks like this. It's a relatively simple form.
Sorry, is this in a particular gauge or something, or?
This calculation that I'm just saying now is not in any gauge.
Oh, but this object is gauge invariant and so on. This gamma gamma.
Yeah, this, yes. This form is basically you have to add a particular boundary term to the integral root minuses r in order to get to this.
So the particular boundary term that you're adding, you have to extend it in some way to the bulk to get this form, I suppose, right? So just the boundary term will just be like an integral on the boundary of the manifold. You want to write it as a divergence of some bulk term or something, is it?
Yeah, it's exactly. It's like a GHY term.
Right. So then they extend the bulk boundary term into the boundary. You could extend it in any way such that at the boundary it matches the GHY term. Is that the? And there is one particular choice that gives this.
I think so.
Okay.
Right. Exactly. There's one particular choice which gives this form precisely. Yeah. Thank you. Yeah. Thanks. Actually, explained it better than I was. Thanks. Okay. Great. So. Yeah, this is J alpha in this. For one can also work out J alpha and say QED or something. And in fact, in QED, the example is super simple. It just looks like J alpha QED just looks like, I think it's just delta F alpha beta wedge A beta. That's it. Anyway, so okay, we are not discussing QED now, but if needed, we can look at the analogies of that. Anyways, so once we have J alpha with us, we can compute what the symplectic form is in 4 dimensions and in 6 dimensions. In 4 dimensions, the calculation is actually super simple. It's
Chandra, can I just ask a question?
Yes.
So did you say once you go to this form, you don't need any additional boundary terms? Say you have a boundary.
Well, the symplectic form will be insensitive to those the extra additions to that.
Right. But I'm just following up on what Anish asked. Like if you're working with this action, is it the case that you don't need to have any additional Gibbons-Hawking term?
No, it's so okay. You're not going to start off with this action. You're going to start off with the usual action and choose a variation such that it precisely matches the GHY, and then gives you just this form in the bulk. So it's not like you would like so you would not start off with this action.
Oh, I see. So but what? Okay, but the statement is not that this is secretly Einstein-Hilbert plus a total derivative, such that the Gibbons-Hawking has already been included in the bulk. That's not the statement.
Yeah, that is the statement. Yes, that is the statement.
Okay. So then you don't have to add any extra Gibbons-Hawking. Is that what you're saying?
Yeah, I mean, you've already taken care of that once you've gone to this form.
Thanks.
That's, yeah. Okay, and anyway, so let's, now we'll just take this equation with us and write down the symplectic form by substituting this metric into that. So if you just take that form and substitute the metric, then we find that in 4D, the thing looks like this, 32 pi g. This is at scribe plus. Again, we could have chose, like we can in principle write down the symplectic form on any Cauchy slice, but here we don't have any massive particles, so therefore we are neglecting the contribution from I plus. Okay, so we just assume massless particles and write it only at scribe plus. There's going to be a slight subtlety which comes in writing this, but that appears in 6 dimensions and not so much in 4D. We'll discuss that when we come across. Okay, so this is it. This is the symplectic form. These are its terms. Now, we could have declared victory here, but at this step, we're going to do something something which might seem weird at first. And by that, I mean that we are going to talk about the boundary values of CZZ. Okay, of this. This has a name, by the way. This is called the shear field. I forgot to mention that. But anyway, we're going to talk about the boundary terms of this, this object. I'm not sure what the initial motivation was to consider this, but eventually I know that they help you in giving the soft theorems. And this is something which we don't have to do in 6 dimensions, or in any higher dimensions for that matter. In 6D, we'll find that the symplectic form has a structure which would look, which does not need you to do, which does not need all this manipulation. By all this manipulation, I just mean that you have to write the boundary terms. Okay. Anyway, so let me just state what I mean first. So what we mean is that this CZZ near the boundary has this particular form. It just looks like some particular scalar object like this. It just looks like an object which is smooth, and it's only a function of the sphere coordinates, and that's it. Okay. Okay. Now, this might seem ad hoc as of now, but it will make sense if once we make the connection with soft theorems. But it'll take some time to get there. So let's just go with the manipulation now and state the final form that we end up getting. However, in 6D, we'll see why it's more natural to, like, why it was natural in 4D to have considered such a thing. Okay, so we have this, and these phi's can also be thought of as, so for example, you can also write this phi's by the following manipulation. If you just take the Fourier transform of NZZ, well, that would just give you this, which is denoted by delta phi ZZ. That's basically phi ZZ plus minus phi ZZ minus. Okay. Okay, great. Right. And now there's going to be another assumption which is made. That assumption can be stated in terms of the absence of magnetic charges in space-time. The absence of magnetic charges in space-time is often more, or the absence of magnetic charges is in general something which we often do in electromagnetism, where we write down the electric field in terms of a potential and so on. In here, in gravity, the conditions of an absence of magnetic charges and so on are imposed by what is called the Weyl tensor. So if you take a Weyl tensor and you set a magnetic, the component of its, the magnetic part of the Weyl tensor to 0, you end up saying that you don't have magnetic charges in your theory. That allows a little more simplification. And the simplification that allows you is that you're allowed to write these phi ZZ as the derivative of a scalar. Okay, that's the assumption. Now, I'll make this point again as something that will become a lot clearer in 6D. I feel that certain things which are done in 4D are not as clearer as it would have been in 6D. Like in 4D, it might seem a bit ad hoc, but in 6D, I feel these things are far clearer. So for now, just take it as the fact that we can further write down phi z z as in terms of a scalar. That's which is the derivative of a scalar. That's it. We call it C plus minus. And in terms of these variables, what you will find is that the symplectic form takes this following form. Oh, I noticed that there's, okay. Dz square, there's a delta of dz square c, wedge, sorry. Oh, sorry, I seem to have missed a notation in my notes. Anyway, sorry. You have delta of dz square n plus 16 pi g du d2z okay. So I should have mentioned this, that dz square n is just defined as so n is basically defined as this. N is c plus minus c minus. That's it. Okay. And this, the hat, the czz hat is so-called the u-dependent component. These things are not so important. I'll just state the physics of this in 1 second, but just for completeness. And all of these details can be found in this particular paper. Let me just mention that in case I'm making some mistake in the notations. So feel free to look at this paper for these notations and so on. But anyway, let's focus on the important part of this thing.
Yeah, Chandra, can I clarify something?
Yes.
So
yes,
this omega is some boundary symplectic thing, is it? Like
I'll just state that in 1 second. Like I'll just state why you have a d2z and not du dz there. But yeah,
even the omega in the first line of this page, like I mean, I see a du integral, not any integral along
yes.
any bulk slice. So I'm slightly confused. Where is this integral being done? It's totally being done on I plus.
It's done at scribe plus. It's totally being done at scribe plus.
Oh, so you're evaluating this omega in some future most time slice, but future most time slice is out of as scribe plus.
So it's okay, good, thanks. I was actually going to mention this while doing the 60 because that's where it becomes more clear, but let me just state it now. So the idea is to just write down omega in some constant time slice. Let's say take this, and then you have to do a manipulation which involves pushing this to null infinity. So the way you do it is by saying that you take u equal to t minus r, okay? And by holding u constant, you take t to infinity. That's the way in which you think of this manipulation. And this thing will become a little clearer when we look at a specific example in 6D. In 4D, it's not, it kind of doesn't play that much of a role. But yeah, did that clarify your doubt or?
Sorry, I didn't follow. You said you fix u and take t tends to infinity?
Yeah, we hold u constant and take t tends to infinity. That's right. We keep u constant as we take t tends to infinity.
Okay.
Sorry, isn't it r? You take r to infinity, u constant, and
yeah, I mean, if you take r to infinity, then t is also going to infinity, right? It's like
okay, I see. Yeah, okay.
If u is constant, then
right.
Yeah, that's yeah. You can think of it as r tends to infinity as well. Yeah, same thing. Great. Yeah, like I said, this procedure of taking the limit of a Cauchy slice is somewhat tricky in general. And in 4D, as far as I know, it plays no role. And there might be an example which I'm unaware of where it plays a role. But in 6D, I know there are definitely examples where it plays a role. And in fact, it was one of the reasons why Wald and others have kind of argued that you cannot have super translations in higher dimensions, but we'll get to that discussion soon. Let's actually focus on the physics part of this equation. The details are not that important. So notice that this omega gets divided into two terms, one of which is a term which has both a du and a dz integral, and the other is a term which only has a d2z integral. I mean, there are some other du integrals, but they're secretly hidden in these definitions of n and so on. But the fact that you can write this in these two forms is going to be crucial. Like, eventually, once we evaluate the charge for the theory, we'll find that you get an integral which is an integral with the whole whole sky plus. You integrate over the whole sky plus, and there's going to be another part which is an integral only on the sphere at u tends to minus infinity. So, which is going to come from this, and this is going to come from this. And okay, these actually have played a very crucial role in certain things, especially in this flat holography business. But we'll get to it in just a second. So once we have the symplectic form, we can use the fact that you could write down QF as just using this prescription, where phi is basically the field G. Let me write down the charge. It's not a complicated thing to compute. Scribe plus. It's going to be F and ZZ and ZZ. In reality, it's just NAB and NAB. That's sorry. Okay. Okay, now this is what's known as the hard charge. This is what's known as the soft charge. And like I said, this soft charge comes entirely from this piece, the one which is not having an U integral, and the hard guy comes from this piece, which has an U integral. This division, as of now, is just performed on the basis of linear versus nonlinear pieces. So for example, this thing has two News tensors. So it's a nonlinear piece, and this thing has a single News tensor, which is why it's a linear piece. Okay, that's the basis of the division right now. But notice one more important thing. For all the symmetries which were known before BMS, which is basically the say the translation and the Lorentz symmetry, this F looks like either y00 or y10. One caveat is that I'm not talking about rotations in this talk. However, there's a entirely different story which where you have to think about rotations and their generalization to what are called super rotations. But that's not going to be a part of this talk. In this, we are only talking about translations and their generalization. So if you had F only as a function of y00 or y10, then dz2F would be 0. So you would have never seen the soft charge had you not taken these translations beyond the ordinary ones. So this is one place where the soft charge comes into role. Okay. A similar thing would also happen in higher D. We'll also have a similar distinction in higher D, but I feel that the procedure becomes a bit clearer. But okay, now this charge is so-called the conserved charge for super translations. And this can be used. We will show it in some detail as to how this is used via the word identities to get the soft theorems, which we will hopefully either do tomorrow or maybe, I'm not sure if we'll get time today towards the end, but okay, we'll probably see that tomorrow as to how this gives the soft theorems. And okay, this we can study the commutators of these charges with the fields and so on and see how they generate this. But this more or less ends the discussion in 4D. There's nothing more to notice now. But like I said, this division is going to play a very important role once we start looking at word identities corresponding to these charges. So if there are questions.
Yeah, Chandramouli, there's a question in the chat.
Yeah.
Can you
Yes.
explain once why we call this the hard / soft charge? Has this got something to do
Yeah,
with the energy?
excellent. Yeah, it does. It does. In fact, yeah, thank you. Thank you for the question. I was going to mention this more for the 6D case, but let me also talk about this now. Where did I write the equation for MB? Okay, maybe it's here. Okay, great. So you see, MB, like I said, the Bondi mass aspect, that is literally a contribution of the stress tensor of the theory. It's like TUU, for example. And notice the structure carefully, which looks like del Z, or maybe I'll just copy paste this here. But yeah, the short answer to your question is yes, this has something to do with energy. The long answer is this. So if you just take this guy, and you actually end up studying this object, FZMB, okay, DOD to C, then what you'll find is you end up getting the same thing as QF. It's exactly the same expression, but this thing takes care of the energy of the gravitons, and this part takes care of so-called the soft part of the gravitons. As of now, like I said, this division is performed on the basis of terms which are linear in the news and non-linear in the news. But in 6D, we'll see this in very great detail. Like I said, in 4D, because of the fact that you have to add this boundary condition here, things may look a bit ad hoc until we go to the soft charges. But in 6D, it's going to become a lot clearer. But yes, this has to do with energy, and this is the main reason. In fact, this hard charge, what you have, the hard charge is exactly equal to the stress tensor convoluted with this function Fz. This is what's giving you the hard charge. And notice that for the hard charge, you have to integrate over all of u. So you have to integrate over all of u. And that actually means that you have to take care of the energy of all the particles which are reaching here. So that's an so that clearly tells you about how this is related to the energy. And the soft part is the meaning of the linear term is not so clear in this, but it will become a lot clearer when we talk about the soft theorems. We'll essentially find that this gives you a term which is which eventually gives the soft factor, which we all recognize.
Chandra,
yes.
Could you repeat that comment about what generated the super rotations?
Thanks. So here, when I wrote the solutions for this equation, for these the equations for, yeah. This is not the most general solution. Okay, you would the most general solution also has some more structure in here. So for example, let me tell you the solution in 4B, to the more general solution, and I would encourage you to look at this 2019 paper if you want more details, this 1906 paper. Just give me 1 second, please. Just look at where this psi was. Yeah, so for example, this psi A. Okay, let me not write psi A like this. So this psi gets these additional terms like.
Basically, it gets U-dependent terms.
Not only U-dependent terms. I mean, yes, sure, there are some terms which are U-dependent, along with some extra structure. Exactly. Along with some extra structure.
Okay, so I had one more question.
And this U.
Okay, go on. Sorry.
Go on. No, I was just going to say that these handling the U-dependent terms is kind of tricky, and we'll do a similar manipulation in 6D. But anyway, I just wanted to say that handling these U-dependent terms are usually a bit tricky. But okay, go on.
And is the hard charge you wrote down bounded? Like,
well, it's yeah, good. So you have so this NZZ should fall off in a specific way when which ensures that. For example, here I think NZZ with U falls off as 1 by U 1 plus epsilon or something, which ensures that this is a convergent integral. We'll see this appear in
what I meant is, are they like, do they have some positivity bonds or something like?
Good. So a general charge. Sorry, I do not know the answer to that. That's a good question. I thought there was some positive energy theorem which Witten had, right? What I mean, does that help you?
Yeah, I mean, it almost looks like that, right? That's why I asked.
I see. I see. Okay. Right. Yeah, I haven't. I cannot. I shouldn't immediately say yes or no because I don't know. But yeah, I'll get back to you on that. Okay. If there are more questions, we can talk about 4D now. Let's go to the more interesting stuff, which is 6D. Great. Sorry. Yeah. Okay, so we almost everything that I said in 4D goes through to 6D, but a few, like in 6D, like I said, certain things become complicated. So one advantage of working with 4D is that because of these fall-off conditions, which we had here, combined with the equations of motion, you would be able to find that the theory becomes asymptotically free. Okay, let me mention this. So in 4D, one huge advantage is that the theory is asymptotically. So I should put this in quotes because at least to the leading order terms that we need, we don't need to consider a nonlinear theory. So by this, I just mean that there's effectively no distinction between a linear and a nonlinear theory in 4 dimension, at least till the order in which we are working in. However, this thing does not hold in 6D. In 6D, there are certain nonlinearities which survive. So there are some nonlinear terms which basically which survive and start screwing up stuff. Okay. Let me say the first place where this happens. So in 6D, first of all, yes.
You have 15 minutes left today.
Okay, 15 minutes. Okay, that's good. I think I can cover the major points. Like I'll not do any main calculations. It'll just be equivalent to just extend the formulas.
Oh, great.
Okay. Okay, great. So like I said, there are certain nonlinear terms which survive and start screwing up stuff. And what are these things? So in 4D, we discussed that the free data in 4D was given by CZZ and CZ bar Z bar. In 6D, however, we have CAB and a tensor DAB, which plays a role. This is nothing non-trivial. They are just parts of the expansions of GAB. So GAB is R square gamma AB plus RCAB plus DAB plus EAB by R plus so on. We don't need the other terms, just these are sufficient for us. Now, what happens in here is if you evaluate the RAB equal to 0 equation of motion, then the leading order equation gives you that del U CAB is 0. That's it. It doesn't constrain CAB in any other way. There is no other equation which constrains CAB in some other way, but only RAB does. And this tells you that CAB does not depend on scribe plus and it has no radiation content. However, DAB is not constrained. So I think if you evaluate this at order 1, then it gives you the del U CAB equal to 0. However, at order R power -1, this gives you 0 equal to 0. And at order R power -2, it gives you the equation for del U EAB equal to something. So DAB is not constrained. That is, there is no equation of motion or the gauge condition which can constrain the value of del U DAB. So what you will find is that if you use the Bondi gauge conditions, then you'll end up evaluating the traces of these C's. So you'll find that CAB is traceless, but DAB is not. DAB looks like, I think it's half CBC, CBC, and so on. There are some more expressions we can write down. But the net point is that DAB and CAB together constitute the free data in the theory. Okay, so the free data here is just CAB and DAB. Okay. Great. In fact, I should say it's the trace-free part, but that's fine. And the new tensor, NAB, is now defined as del U DAB. However, notice that the definition of the new tensor is not unique, because you can always add some function of CAB to this. Since the derivative of CAB is 0, you can always add any function of CAB and still get some new d tilde variable, for example, where d tilde would be DAB plus some function of CAB. And we'll see how this has played a very crucial role in understanding this. Okay, good. So now if you work the super translation generators out, what we will find is that xi u is still f, like we had discussed in 4D. Xi a, again, we're neglecting rotations. And this is an expression which is valid at all orders in R, e power 2 beta GAB dr prime. And xi r is r by 4 ua del f minus del a xi a. So this is an equation which is valid at all orders in R. If we, in fact, this is D. So if you plug D equal to 1, you will recover the xi that we had before. Okay, and we can compute the variation of CAB. So using these, we can compute what CAB is, and that just gives you minus 2 del A. In fact, it's valid in sphere, so it's del A del BF minus 1 by 4. Okay, and the variation of DAB, however, is fairly complicated. So DAB takes this form. It's a big expression. We don't need to look into the details. So I'll just use some function that's, I don't know, some function P of F and CAB. It's some bilinear of bilinear which is composed of this. Now, this equation is a problem. It's a problem for the following reason, and it's a problem which arises only in the nonlinear theory. Had you been dealing with a theory which was linear, sorry, which was linearized about the metric, for example, if you take CAB, DAB, EAB, and everything to be just linearized about gamma AB, then P is just 0 in linear theory. However, in the nonlinear theory, it's not. And the reason why this is the problem is it's related to what Akhil was asking before. That's about how the how certain things become divergent. For example, if we assume this, and like if we assume that this expression is true, or if you just, sorry, there's a typo, just f del u, yeah. If you just go with this expression, then you would find that delta f dab has terms in it which are u independent. So these guys in here, there's a u independent term. It's u independent just because del u CAB is 0, which was an equation of motion. Therefore, this term is u independent. And this tells you that this object, as you take u tends to plus or minus infinity, grows as u power 0. However, we find that this fall off is too strong. It's too strong in the sense that if you assume that DAB goes like this, or the variation of DAB goes like this, then you would find A, the symplectic form diverges. And it's simply because an integral of DAB or delta f DAB would now not be convergent, because if you have a function which is becoming a constant at infinity, that would not be that would make it diverge. And B, you would find that this is also violating the saddle point approximation. So I think I've just got 5 minutes, so I'll just state how this is resolved. And anyway, so it was because of these two papers, these two reasons that the papers by Andrew Strominger and also Ankit Agarwal, like they explained it in detail, especially in Ankit's paper, that why the nonlinear theory is not going to work in high dimensions. This is only in 6D, but a similar problem also exists in 8D and so on. Like I said, such a thing does not happen in 4 dimensions. In 4 dimensions, there was no term which had this complication.
Chandra, what saddle point approximation are you referring to?
Yeah, maybe I'll discuss that tomorrow. But it's just it's basically how you look at the behavior of the graviton mode. That's it. It's just the graviton. It's like you expand H mu nu in terms of its mode expansions, and you just perform the mode expansions and the integrals on that by looking at the behavior you expect from the soft theorems, and you will find that DAB should, like the large U fall off of DAB should go as 1 by U square. This is the outcome of the saddle point approximation, but we'll discuss in more detail tomorrow. Thanks for the question. But yeah, this is it. This is what I mean. Like you just do a saddle point approximation to the mode expansion. That's it. So anyway, so the resolution to this is as follows. We just define a field d tilde AB, which looks like DAB. I think it has a -4. Okay, this form is not so important, but let's just call it some function AB, which is only a function of C. In fact, it's a function of C square. That it has C and C squared in it, and it's a very simple structure actually. In fact it's just -4 C CAC CBC plus a trace term. It's not so important, but okay, it's some structure like this. And you'll find that DAB is trace free, and also once you compute the variation of DAB, you'll find that it's just F del DAB. D tilde AB, sorry. That is, this contribution of P is sucked up by AB. And the reason why you're allowed to do this is because we could add an arbitrary function of CAB to DAB such that we don't change the News tensor. So the News tensor is still del U DAB is equal to del U D tilde AB. Okay. And once we do this, we actually find that both of these conditions match. And we also can obtain a finite symplectic charge, finite Noether charge, and also see how it matches with the Bondi mass and see how basically the IR triangle generalizes. But okay, I think I'll stop here for today. We'll basically continue from here and just discuss how all of this is related to the soft theorems tomorrow. I don't think we'll need the third lecture, but yeah, feel free to ask more questions if you have now.
Can I ask a question?
Yeah, please go on.
So what exactly was this freedom again? Like to redefine the D, I mean,
yeah,
how
so
do
this,
you think of it?
Yeah, so like I said, so in here, what you had was like, your CAB, which was which plays a special role, which I think will become clearer with the soft theorem. But the fact that CAB is U independent, okay, tells you that the News tensor which you define, which the News tensor basically characterizes the radiation, and also from a 4D calculation, you see that the News tensor is what appears in the hard charge and everything, like in here, or even it comes in the soft charges. The News tensor is invariant under a redefinition of DAB. So what this means is that instead of having started an expansion in this way, had somebody started an expansion like R squared gamma AB plus RCAB plus D tilde AB plus EAB and so on, then you would have never seen this. You would have never seen the problem which was first pointed out in Ankit's paper. Okay. So had you started working with the correct variables, you wouldn't have seen this issue. That's the meaning of this.
But is there a I see that you can cook up this AAB function and get rid of those extra u⁴ terms in DAB, but
Yes.
What kind of was there? Is it a gauge choice? I mean, are we making a gauge choice? Are we making fixing some residual gauge or something? Is there some invariant statement like that?
I don't know if it's a gauge choice or not. I mean, I'm not sure if I should call it a gauge choice, but it's more like, you know, if like I said, instead of having the function DAB here, suppose you just started with DAB plus an AAB, then you wouldn't have seen it. It's just a different way of expanding. I'm not sure if we should call it a gauge choice, but it's and it doesn't affect the radiation content of the theory, like the radiation and the hard charge and everything is still written in terms of the newest tensor, which is invariant under this redefinition. As of now, you can just think of it as a field redefinition that helps. It's instead of
field
labeling
redefinition, which is non-linear in all these components, right? Because,
exactly, a field redefinition which is non-linear in CAB.
Yeah, I'm just wondering, was there I mean, how to think of it physically, like, or I mean, I don't really understand when you shift DAB, what are you shifting?
Oh, good. So okay, great. So actually, you know, there's an equivalent way of stating all of these things in the quantum language, and what's true is that the CAB parameterizes so-called, you know, the vacuum you select. For example, because of these IR properties, you end up having an infinite degeneracy of the vacuum state, right? And CAB is the one which labels this in 6 dimensions. In 4D, it was this auxiliary variable phi, which played the role of a boundary term, this guy, but in 6D is basically CAB. So the statement is that if you go to some different vacuum, that is, if you choose a different vacuum, then the graviton, physically the graviton is given by the variable d tilde. Now, if you want to think of it in a classical sense, what you can think is, say if you're linearizing the, say you start with the metric r square gamma AB plus, just r square gamma AB, and then you perform a super translation. You initially had CAB equal to 0. So your G1 was something where you had no CABs, and you go to a G2 where there was a CAB. And this is something you would just obtain by seeing that delta F CAB is looks like, you know, minus 2 into del A del B F minus some del square F, some delta AB del square. Anyway, this is, you can just perform a variation on this and go to a metric which has non-zero CAB. Now, once you're in this metric, you can think of expanding the you can think of studying the gravitons even linearly in this metric. And if you start thinking of the gravitons as a linearization about this new metric G2, you would find that the correct way to label the graviton is d tilde and not b. Does that help it, or I'm not sure if I'm making
yeah, kind of. Yeah.
And in the quantum language, just like you choose a different vacuum, like depending on the vacuum you're sitting in, you have to use the correct DAB to label your gravitons. That's the outcome. Yeah.
Yeah, thanks. Yeah, that helps.
Okay.
So all these statements immediately generalize to 6 and higher even dimensions, or?
Good. So in higher even dimensions, what would happen is here the gravitons were only characterized by CAB and DAB, but in higher even dimensions, what you'd have is EAB would play a role. In the paper in which we are working in, we haven't given a form of how these functions AAB looks like in higher D, but I'm sure there should be a good way to work it out in all general D. We have not worked it out. We have only worked it out in 6D. But
is there some simple way to see that, like if I go to 8 dimensions or something, both C and D will become U independent, and you have to really look at E to construct news. Is that what you're saying?
Good. Right. That's
Or is that
precisely
right, or
what
is
I'm
there
saying.
some story like that?
So let me say the following. I am unable to recollect if in 8 dimensions you have del u CAB equal to 0 or not. But as far as I remember, in 8 dimensions, del u DAB is certainly 0 in 8D.
I mean, probably up to that follow-up should be 0, right? And then probably
yeah, up to that. Yeah, that's what I would have expected. Yeah, correct, exactly. I mean, yeah, like in 8D, this statement is certainly true that EAB does not have a equation of motion. That is, if you try to work out the RAB equation, you just get 0, 0 for EAB, and you're able to find del F in some things. So it is, but I'm not sure which of these 3 gets redefined. I would only expect EAB to get redefined. Since EAB is containing the radiation,
right.
I would
so
only
probably you
EAB
have to take the background metric up to D and construct the corresponding E tilde or something. Is that?
Yeah, either. So I should say one of, like either what you're saying is true, or you just have a E tilde AB, which is a function of EAB and DAB alone. Maybe CAB doesn't appear. That's I'm unable to confirm between these 2 possibilities. It's one of these 2. Either what you're saying is true, that EAB tilde is EAB, DAB, and CAB, or CAB doesn't appear. There's something I can tell you tomorrow.
Thanks.
But I have to look at the equations once. Yeah.
Any other questions?
If no one else is asking, can I ask one more question?
No, you can't. Okay, go ahead. Since there's no other questions.
I don't know. The senior most postdocs are bullying lower postdocs or lower students. Okay, cool. So could you repeat that comment you made about this magnetic charges and so on? You said something with some difference in 4D, 6D, and so on. I didn't understand it. Thanks.
Yeah. Okay, great. Yeah, I'll anyway repeat this in some detail tomorrow. But there's this particular component of the Weil tensor, which so-called gives you the magnetic part of the Weil tensor. I don't recollect exactly which component this is. Just give me 1 second. I'll just look it up. Put it in my notes. I mean, the electrostatic analog is just that the curl of A is 0. It's a statement of that sort. But in magnetic,
yeah, that was crucial to write the difference of U as U as gradient of this phi and so on. Right? I mean, sorry, C as gradient of phi and so on. Right?
Exactly. That's the. I mean, it can also be motivated in one more way, actually. In fact, yeah. Let me also say it in one more way. So it's like, when you transform this delta FCAB, you end up getting a transformation of this kind. I want to write that here. Let me just. So it's like delta AB del square F, something of this sort. Okay. So here you would notice that this kind of affects this in a very nice way. So this term is not that important for us. That's just saying that the trace of CAB is 0. This is the extra term. But if you just take the part which is, major, which is this, so it just says that CAB, upon varying with the super translation, gets varied by a scalar function, by derivatives acting on a scalar function. Now, in CAB, CAB here is a function of the 4-dimensional sphere. Okay, or in 4-dimensional, like if you decompactify the sphere, it's like a 4D flat space kind of thing. Then you can, in principle, you could have expanded CAB in terms of these tensors, right? You could have expanded that in terms of these, what are these called? These some decomposition, right? This Ishibashi decomposition or something, maybe like you decompose in terms of these vector harmonics and so on and so forth. But upon doing that, you just find that only the scalar mode is the one which gets affected in a super translation. That kind of motivates you to set the components proportional to the vector or the tensor harmonics to 0. That's one way of looking at it. And so by which I mean, if you just write down CAB as this thing here, like just think of it as a pure gauge symmetry, where you just write it in terms of psi such that delta F psi is just F. Then you end up getting delta F CAB is that. And you would also find that such a restriction comes by imposing the magnetic charge constraint, which is saying that a particular component of the Weil tensor goes to 0. Unable to recollect which particular component it was, but it implies this condition at leading order. This is 0, which further implies this, where UA is some derivative of CAB. So UA is like del B CAB kind of a thing. And this is an equation which satisfies that. So you need both of these things. You need the fact that the super translation only changes this scalar mode in CAB, and this magnetic charge constraint which imposes this. Now, in here, this is not going to be that important. Like, we could have done all of this without ever talking about this variable psi, but it's just good to know that CAB is not having a huge set of degrees of freedom, but is just labeled in terms of 1 degree of freedom psi. That's, and this has a name, by the way. It's called the Christodoulou-Kleinman conditions or something, CK constraints, which often people impose. But this is it. Like, did this answer your question, or did I confuse you more?
Yeah, probably too much details, but thanks. Yeah, it's good. Thanks.
Okay, all right.
Any other questions by someone not named Akhil?
I think there's only one person named Akhil. Okay.
All right, if there are no questions, let us thank Chandramouli. Thanks, Chandramouli, for the excellent introduction. And we will see you tomorrow again.
Yeah, it's the same time, right?
Same time. I will
Okay.
send you the link.
Okay. All right. Thank you. Thank you very much.